see your slides, but we don't hear your voice.
Okay, can you hear me now?
Yes,
Hello?
we do hear you. A little bit weak, so try to stay close to the microphone if you can.
Okay.
Okay.
I'll speak loudly. Okay, as you mentioned, this project has been developed inside the iHeart project and has been developed in the facts library. It regards myocardial perfusion. So it's great that I present after Simone because of this amazing presentation. And I'll try to delimitate the problem. So the physics of interest are the blood supply of the heart. So in particular, you see in the figure in the right that coronaries stem from the aorta and deliver blood to the heart. This, if we're able to capture the inclusion of blood in the tissue, we can further improve the modeling of ischemia and really open a door to considering things inside blood such as sugar for diabetes and then go deeper into metabolism models. So this is the relevance of going into nonlinear fluid mechanics. I really want to narrow down the parts of interest. So for this, we consider the aorta, okay, as its pressure as a driver of flow. Blood goes through the coronaries to the tissue. Okay, this is oxygenated blood, and then in the myocardium goes through arteries, capillaries, and then veins all the way to the coronary sinus to the right atrium. This small heart represents the rest of the journey of blood. So there have been many developments on hearts that are static, and the main objective of this kind of model is to incorporate deformation into this. So the scope of this work is to have flow induced by the aortic pressure. Okay, in particular, we use this kind of results in the right that can be obtained from circulation models coupled with mechanics. Then this blood gets distributed into the tissue, and finally the blood leaves the tissue through the veins, and this is the end of the circuit that we're considering. Just to give you the kind of result that we're expecting, here we see a deformation, a contracting left ventricle, and we can track the evolution of the total blood inside the tissue. Okay, separately between the arteries and the capillaries, and also considering both, we see the total variation of mass. Okay, for this, of course, we make some assumptions. We consider a continuum model. So we have, as in mechanics, the myocardium, okay, the cardiac muscle, and then we consider also condensed pointwise the arteries, okay, and the capillaries. We're going to see in a while why I'm not considering the veins in this. And the relevant quantities that we need to study here are as usual, the displacement, okay, and all its relatives, the strain transfer and its determinant. And then we have this quantity called porosity. It represents the percentage of fluid, be it in the arteries or the capillaries. But this is not really a natural variable to consider in this kind of models. Actually, the one that comes up after studying the thermodynamics is the reference porosity, which comes from this very simple derivation. So I'm going to use the reference porosity throughout the presentation. Its interpretation would be the fraction of fluid present in a deformed portion of the tissue. Okay, now I'll present how the nonlinear elasticity equations are composed. First of all, we have our conservation of momentum, and this is, let's say, more standard from nonlinear mechanics. We have our Piala stress tensor plus an active stress. I can consider the mechanics in this level of generality. Of course, the active stress can consider ionic models, but at this level, it's not important. The important thing here instead is that the pilostrous tensor depends on the capillaries. Okay, and I'm denoting in green quantities that need to be solved through constitutive modeling. What we consider in addition to that, here's the conservation of mass in each compartment. So the variation of our porosity, of our reference porosities in each compartment is going to be given by a nonlinear diffusion, which depends on the pressure. The pressure at its time depends nonlinearly on the on the strain tensor and the porosity. We have that our compartments, so our arteries and capillaries interact, and there's a source and sink term. In particular, how are we coupling this model to the coronaries? Okay, we're considering a 0D model for the flow from the coronaries, as we're not, so we're neglecting the complex fluid dynamics that they present. And this is coupled to the mass conservation through, in the arteries, we get the flow from the difference pressure between the pressure in the aorta, which I said before, that's the pressure that guides the blood flow, and the average of pressure in the arteries. Okay. Instead, in the capillaries, we get a sink term, which is proportional to the pressure in the capillaries and the pressure in the veins. So this is actually the reason why I'm not considering a separate compartment from the veins. The pressure doesn't have very high spatial variation, so this is a good approximation of interaction between the capillaries and the veins. We still need to define what happens with the pilostrous tensor and the pressure. And this happens through constitutive modeling. In particular, we see that the pilostrous tensor is given by the derivative of the energy with respect to the strain. This is the same as in nonlinear mechanics, and I usually consider this as a generalization of the energetic framework. So we have pilostrous tensor here, and here the pressure is also given by constitutive modeling. We have exactly the same potential. We take its derivative with respect to the porosities to obtain it. And one very important thing is here that pressure is actually not a variable. It depends non-linearly on the fraction of each compartment, and this has been studied long ago. So here on the right, you can see actually the kind of dependence that the pressure has with respect to the local volume of blood. So to capture correctly the physics, we really need this kind of nonlinear models. We propose extending another energy. So let's say the modeling here is quite an open field. Work developed by Chapelle and Moreau considered the first mechanical contribution and the third one, which depends on Ps, which is the reference solid porosity. Okay, so here we consider the percentage of tissue, which is of course it's one minus the other porosities. But we consider also the addition of energies depending on the local porosities. The advantage, so there's a list of advantages. One of them is that this term on the right works as a barrier function for our porosity to make sense, which is it's a percentage, so it should be between 0 and 1, and we can actually achieve this through this kind of model. Then we get accurate or realistic interaction between the physics. So actually the mechanics have a pressure contribution from this term depending on the pressure, on the solid fraction, on solid porosity. And what I would deem the most important consequence of this kind of model is that the pressure felt by each compartment, so capillaries and arteries, is actually given by its pressure minus the one in the tissue. So this kind of additive decomposition naturally gives this kind of response. So that this transmural pressure, be it in each compartment, is exactly what we see, and in fact, this, for example, is psi I depends on the fluid portion of this compartment minus the intramural part, which regards the tissue. So from the point of view of the physics, it makes sense, and we get finally this kind of constitutive loss. Okay, so in this case, the psi out, which depends only on F, is going to be, for instance, a classic quasi-compressible Guccione material. Okay, with this, we can perform some numerical simulations. We still go on with further assumptions to speed up this, to speed up the framework. So, for example, we consider the coupling of the mechanics and the perfusion. So, mechanics, of course, guide perfusion. The formation is important for the blood flow, but we neglect the feedback of blood on the mechanics. That's in one part. To simplify numerical schemes with respect to the serial D flow from the coronaries, we consider a staggered scheme, which you can see, for example, in this case. So this would be the arteries. And the final point, which is a little bit delicate, but I wanted to mention it, the flow of blood due to contraction is largely guided by the gradient of J. So if we have, say, a P1 approximation of the mechanics, J is going to be depending on the gradients of displacement, and then getting another derivative is going to make this term disappear. So one solution would be using an expansive P2 or higher order elements for displacement. But in this case, the decoupling allows us to project the J and get the same kind of phenomenon. Okay, now for the results. The one great thing of decoupling the mechanics is that we can compute it as a pre-processing stage. This is the actual result that we get, which serves as validation. Then also this model is coupled with circulation, which gives the pressure in the aorta, which is then going to drive the flow through the compartments. Here instead we see the solution of the conservation of mass, and on top there's the pressure in the aorta, which is the one that guides the fluid, guides the flux. And instead, for example, in red there's one in the arteries, and in purple in the capillaries. One interesting feature is that at the systolic peak, pressure starts decaying quite fast. This is actually due to the difference of pressure generated by the contraction, so that blood starts flowing faster, and this is indeed a reasonable result. And lastly, we can see defining this quantity, that it gives the variation of local density in each compartment. We can track what I've shown in the beginning, which is the evolution of mass throughout the tissue. If we use this to compute the flow in each heartbeat, we get a total flow between the arteries and veins of 3.14 milliliters per heartbeat. Actually, the physiological value is 3.3, which was measured, and we recovered this value only through simulation. So now that validation is a huge subject, this number gives us a good validation for this model. So to wrap up the presentation, I presented an in silico model of coronary circulation. Okay, it includes the compliance of material parameters, and it presents all the required features to couple in a physically relevant manner the mechanics and the blood flow. We have set up the computational scheme in a way that allows for solutions in hours. So we consider a CRD model for the coronaries, and then staggered decoupling to be able to solve this nonlinear conservation of mass problem. And then the fact that the mechanics is decoupled, but that we're still obtaining a reasonable blood output gives the message that this can be easily coupled into existing electromechanics software. So the only thing that you need for this is to compute mechanics and from it get a aortic pressure. Now the results for the results to present a more accurate spatial variability, we definitely need to consider perfusion regions as explained before by Simone. So this is the absolute not future work, but actually present work. We're doing some developments in this regard. And the mathematical analysis is completely open. I just want to mention this. So that concludes my talk. Thank you very much.
Thank you, Nicolas, for the interesting contribution. Any questions from the audience? I have maybe in case anybody? No, I have a quick one. So definitely you spent a lot of work on the, let's say, on the nonlinear model. Can you comment on what are the key points, what the nonlinear model brings with respect to perhaps other options that would have been to use just the linear BO poromechanics equations? So what's really the key that of the nonlinear model that allows to reproduce correct perfusion dynamics?
Okay, yes, understand. Let me start. Let me start here. So one thing is that actual measurements of the variation of pressure have shown that the variation with respect to the mass is nonlinear. So in any case, the use of a linear model is not going to capture the entire spectrum of variation. So, but for example, if we were interested in a really small portion of this kind of function, then maybe a linear model would be suited. But this is not the case. There's particularly the capillaries have a huge variation in the amount of blood that flows through them. So that's the purple curve. So we see that this is actually not the case, and it has also been validated through transmural results performed in other works by Chappelle and his collaborators. So that's from the point of view of the physics. I wanted to give another intuition for this. It is that if we use a linear model, we would kind of use quadratic energy here. Okay, using quadratic energy doesn't allow us to obtain these barriers, so that we would not be able to keep our porosities between 0 and 1, and it wouldn't be physical. Porosities can get really close to 0, so we would absolutely lose that kind of behavior.